Alright, so in this video I'm gonna be explaining another important article about domain adaptation, and the title of this article is Exploring Covariate and Concept Shift for Detection and Confidence Calibration of Out-of-Distribution Data. So this paper in 2021. Moving beyond testing on in-distribution data, works on out-of-distribution detection have recently increased in popularity. A recent attempt to categorize out-of-distribution data introduces the concept of near and far out-of-distribution detection. Specifically, prior works define characteristics of out-of-distribution data in terms of detection difficulty. We propose to characterize the spectrum of out-of-distribution data using two types of distribution shifts, covariate shift and concept shift. Where covariate shift corresponds to change in style, for example noise, and concept shift indicates the change in semantics. This characterization reveals that sensitivity to each type of shift is important to the detection and confidence calibration of out-of-distribution data. Consequently, we investigate score functions that capture sensitivity to each type of dataset shift and methods that improve them. To this end, we theoretically derive two score functions for out-of-distribution detection, the covariate shift score and concept shift. So we have for concept shift, we have concept shift score. For covariate shift, we have covariate shift score. And they are based on the decomposition of this KL divergence for both of them, of course. And propose a geometrically inspired method to improve out-of-distribution detection under both shifts with only in-distribution data. Additionally, the proposed method naturally leads to an expressive post-hoc calibration function, which yields state-of-the-art calibration performance on both the in-distribution and out-of-distribution data. We are the first to propose a method that works well across both out-of-distribution detection and calibration and under different types of shifts. There are three contributions. We propose to characterize the spectrum of out-of-distribution data in terms of covariate and concept shift and unify the notion of near out-of-distribution data in out-of-distribution in different literature. To represent distribution shift, we analytically derive two score functions based on KL divergence to capture both shifts more effectively. To model distribution shifts, we propose geometric ODIN to improve sensitivity of the neural net during training and calibration during inference. So model calibration methods can also be largely divided in two categories. Training time calibration using augmentation, using modified losses, and post hoc calibration. So confidence calibration refers to aligning the maximum predicted probability, the confidence, from multi-class classifier to the empirical accuracy of predictions. For example, if a classifier classifies 100 images to the label dog with a confidence of 0.8 for each prediction, then 80 out of 100. So you see in this picture the illustration of near and far out-of-distribution data. The top left is the CFAR, this one is CFAR, dataset for training. The top right, it is the CFAR 100. So here is CFAR 10, and here the right is CFAR 100. And also the lower left is the corrupted CFAR 10, and the lower right is the Street View dataset. So 80 out of 100 those images should contain a dog. So we adopt the definition of this reference to define confidence calibration. So p hat is a probabilistic multi-class classifier for m classes. So we map it to these m classes. For any input, so it's just a m-dimensional probability vector. So we have m classes. So it's a multi-class classifier. And the probabilistic classifier is confidence calibrated if for any p in this interval 0 and 1, we have the probability that y to be argmax of p hat, condition of maximum of p hat equal to p is p. One notion of confidence calibration is the expected difference between confidence and accuracy. So expected calibration error is a metric that approximates these expectations. ECE partitions predictions into several m equally sized bins. Because we had m classes, so we partitioned it into m equally sized bins. And then we calculate the average accuracy and confidence for each of these bins. And so y hat and p hat are the predicted class and confidence of an input x with corresponding label. B sub n denotes the nth bin. The accuracy and confidence are calculated. So this is the accuracy, this is the confidence. So this expected calibration error is defined as a weighted sum of difference between confidence and accuracy in each bin. Therefore, the lower expected calibration error indicates better calibration. So it's the difference between this accuracy and the confidence for each of the bins, because we have n bins. So this is the diagram of score functions. Because we have, for covariate shift, we use this covariate shift score function. For concept shift, because it's not only dependent on data, but also it depends on the label. So it's a two-dimensional. It's a concept shift score. And then now that we have the features after giving the neural network, we have this geometric ODI-N training. And loss is then backpropagated to all components during training and only to alpha and beta during calibration. So as we see in this figure, the first goal is to derive score functions to represent the shift in either probability of data or probability of label given data. We denote the score functions by covariate shift score and covariate shift So we propose a geometrically inspired out-of-distribution detection with only in-distribution data. And the third goal is to show that, unlike prior works which treat OOD detection and calibration separately, our proposed method naturally leads to an expressive calibration function in the family of intra-order preserving functions. So we theoretically derive two score functions, G and H, based on KL divergence between uniform distribution and a predicted distribution, and M is the number of classes. By starting from KL divergence, we hinge the subsequent derivation of score functions on a physical meaningful uncertainty measure, how far the predicted distribution is from a uniform distribution. This relationship ensures a natural interpretation of score functions because predictions on distribution shifted data should have larger uncertainty, smaller distance from uniform. And we are specifically interested in softmax linear models for classification. They typically consist of feature extractor and a linear layer followed by softmax. So the output of the linear layer logit is just an inner product between the feature vector and weight matrix. And this one is the ICE logit. And P sub I is the predicted, this P sub I is the predicted probability of the ICE class. So we can use the inequality property of log sum exponential function, and the KL divergence can be bounded. So KL divergence this is the lower bound and this is the upper bound. But the upper bound is just this maximum of loss, which can be further decomposed into two multiplicative components, and that's why it is theoretically justified that how we created these score functions for both concept shift and covariate shift, because we define the covariate shift score as just the norm of F. The norm of F. Because F is just the feature vector from feature extractor. So when we say G of X is the norm of feature vector, it only depends on the input. So we get input goes to the neural network, we have feature extractor, this is feature extractor, so we get F, then this norm becomes the norm of feature extractor. So activation of a neural network on a covariate shifted data should be weaker than in distribution data. So G of X, this norm, assigns a higher value to in distribution data than to out of distribution data. And we define the concept shift score as the maximum of this second norm of weights, cosine phi, minus this weight cosine phi over all M. The summation is on M. And because it is the difference between the cosine distance of predicted class and the average cosine distance of all classes, and depends on both input and final class membership. So as class assignment should be less obvious under concept shift, then difference should be small. So this H, Y, and X assigns a higher value to in distribution data than to out of distribution data. In retrospect, our definition of covariate shift and concept shift scores supports existing findings that the feature norms correspond to intra-class variance, and angles reflect inter-class variation. Covariate shift represents non-semantic change within a specific class. For example, intra-class variance. Concept shift represents semantic changes, inter-class variation. So we formalize the intuition observations as score functions from a KL divergence viewpoint. So the combined score function carries a physical meaning. It bounds the KL divergence between a uniform distribution and a predicted distribution. Intuitively, a small u indicates a large uncertainty because u upper bounds the KL divergence between u and p, and a large u indicates small uncertainty because it also appears in the lower bound. We can derive u by Taylor expanding the softmax function. So we adopt geometric sensitivity decomposition to improve sensitivity to covariate and concept shift. And GSD, this geometric sensitivity decomposition, improves sensitivity by extracting sensitive components from this norm, an angle through a decomposition of them into a scalar offset and a variance component. So a scalar and a variance component, the scalar offsets, the scalar offsets, and C sub f and C phi minimize the loss on the training set, and the variance components account sensitively for variances in samples. With the decomposed components, the original logits can be written like this. And else by denote the new ice logit. So this one is the new ice logit. The new feature f is a direct output of feature extractor and is modified by alpha and beta, and the calculation of score functions is only uses the feature and is independent of alpha and beta. Because cosine of C phi and Cf are scalar offsets, we can parameterize them separately from the main work. Unlike GSD, which parameterizes them as instance-independent scalars, we make alpha and beta instance-dependent scalars and use a single linear layer to learn them. To enforce numerical constraints, alpha uses a sigmoid activation and beta uses a soft plus activation. So this is just the relaxed output. Now the new predicted form and the angle are more sensitive to input changes because they encode variances in samples. So including beta improves sensitivity to covariate shift, and including alpha improves sensitivity to concept shift. So alpha is good for concept shift, beta is useful for covariate shift. The offset scalars beta and alpha are designed to minimize the training loss. Practically, they are optimized to push the predicted probability of ground truth class to be close to 1 during training, and this intended behavior unsolicitedly continues to inference time when accuracy is not as high as during training. Nevertheless, our construction of alpha and beta belongs to a family of intra-order preserving functions, which has potentially strong representation to calibrate complex functions in deep networks. So to prove it, it suffices to show, it is just enough to show that the alpha of 1 and beta forms a strictly positive function. So we just minimize the negative log likelihood on evaluation dataset.